Hello, this is Giovanni Denaro from University of Milano-Bicocca, and I'm going to present to you a joint work with my colleagues Luca, Guglielmo and Andrea Riboni, in which we present a new idea about measuring software testability. Well, testability is the degree to which a software design supports or hardens its own testing. And so, if we could measure testability, we could also make important decisions on how to prioritize the testing effort, for example, for modules that require more testing than others, or in some cases for modules that you may want to refactor or redesign somehow. And at the state of the art, there are proposals for measuring software testability indirectly, either by using software metrics like, for example, lines of code, cyclomatic complexity, class coupling, and so forth and so on, that may correlate with testing effort and quality, or by estimating fault sensitivity, that is the probability of executing, infecting, and propagating faults, which again can correlate with the hardness of testing. But the problem that we see with this proposal is that the correlation doesn't guarantee a causal relation. And in fact, if you look in most papers in literature, there are contrasting results about, for example, which metrics are the best predictors. And another issue is that the measuring of correlation with metrics or the estimation of fault sensitivity are based on existing test cases that we found in existing projects. But this can bias the measurement with arbitrary decisions that were made at the moment in which the test cases were designed with different goals than measuring testability. Well, with this in mind, let me introduce you our new idea on measuring testability in a different way. In a nutshell, we propose to measure testability as follows. Given a set of software modules and relevant test goals, we address them directly with a test generator. Then we reason on the resulting test cases to identify evidences of testability issues, and based on the amount of those evidences, we estimate testability accordingly. We now further formalize this overall idea into a new definition of testability. Idealistically, let's say we know all faults in a software module and all test cases that can be developed for that module. And suppose we also know the relation between which test cases reveal which faults, and we also know how to classify test cases as easy or hard to identify and design. If we have all of this, we can measure testability as the amount of faults that can be revealed with easy test, with respect to all the faults that are executable. And this means that testability is low if there are many faults that can be revealed only with hard test cases. And we can extend this definition to the traditional sub-components of testability. One is controllability. In this case, we are interested in how hard is it to execute the faults. And so we reason on the test drivers in the test cases, and controllability is the portion of test drivers that are easy to identify and design. The other subcomponent is observability, that refers to how easy or hard it is to observe the faults with test oracles. So we reason on test oracles, and again observability is the portion of faults that can be revealed with at least a test case with an easy test oracle. We now move from these idealistic definitions to concrete measurements of testability. We designed a prototype tool to measure controllability and observability, so let me start with controllability. given a set of classes under test, we use the test generator EvoSuite, which is search-based. We run it in 6 passes of 10 minutes for each class, with 3 different fitness functions. And then we refer to the tool measure that makes mutation analysis, means false seedings, and identifies which seeded false are executed with the generated test cases. So we regard to these false as the evidence of false that can be revealed with easy test cases generated out of the box by the test generator. Then we augment the program APIs by breaking the encapsulation, and we run the process again, and this way we identify other seeded false that can be executed with the test generator with some help. So they are somehow in the scope of the test generator, but they are hard to identify out of the box. And we estimate controllability as the portion of seeded false that can be executed out of the box with respect to the ones that can be executed with facilitated APIs. For observability, we rely on automatic generated assertions, and we repeat the process the same way, and we discriminate between the false, seeded false that can be executed with proper assertions with respect to the ones that can be just discriminated by looking at intermediate states of the program. And observability is the portion of seeded false that can be executed with proper assertions. With this prototype, we run a qualitative study. We consider 355 classes from the project closure compiler. We derive the test cases, the mutants executed with and without the encapsulation and revealed with assertions. The qualitative analysis consisted in inspecting the 10 classes with lowest score and the 5 classes with highest score, for example controllability scores, to understand what were the issues and the boosters of testability in those classes. For controllability, we found that 5 classes with lowest controllability implement multi-step interaction protocols that challenge the derivation of test cases. 3 of these classes have complex data structure as inputs, and 1 class is guarded by preconditions that make tests more difficult. 2 classes had no issues, so they are false positives due to limitations of the test generator. All the classes with the highest controllability have inputs of simple types, and for 3 of them, the inputs can be easily set with constructors. We made similar analysis for the case of observability. 3 classes with lowest observability have observer methods that must be called with complex parameters. 3 classes deliver their outputs on system streams that are hard to observe during testing. 2 classes updates private data structures that cannot be observed, and 1 class makes asynchronous updates that are difficult to catch in test cases. Also in this case, we found 2 false positives. In the classes with the highest observability, the output consisted of simple return values, and in 2 classes there were getters for all output values. As a quick recap, I presented our new idea about measuring testability empirically based on automatically generated test cases and our initial prototypes and initial qualitative findings. Let me stress that this is mostly work in progress, so we are now working to refine our metrics and to provide quantitative results, which however require ground truth that we are trying to define. And we also aim to do experiments developers. And with this, I thank you for your attention, and I'll be happy to answer your questions.
Okay, good morning, good evening, good night, everybody. Welcome to this session called Testing General Issues. I'm Claudia Ayala from the Technical University of Catalonia. And in this session, we will discuss 3 very interesting papers. We will start with the first one that you just watched the video, that is towards evidence-based stability measurements. I'm glad to present the authors. We have here Luca, Guglielmo, and Giovanni Denaro that will be so eager to reply to your questions. Let us see the chat. Yes, we have one question from Caroline. She says, thank you for the talk. Great to see in such details on what can be tested with automatically generated test cases. Do you think your results generate 2 human engineered test cases? What will change?
So I would say they are, automatically generated. So definitely there is some limitation that the test generator is not able maybe to catch. Usually we use metrics like, branch coverage or mutant coverage to drive the test generator. But basically the type of test cases that we get are very similar to what a human can generate by calling the legal API of the program. I would say that some of them are even more in depth, with the type of number of calls that the test generator could try to do. That's to say how similar they are to human engineered test cases. But basically our point is still different, because we don't want to use those test cases in the testing process. I mean, we don't maintain that or propose that. We use them to do an estimation. We know that the estimation is done on, let's say, partial state space of the program, but what is our goal, or at least our, let's say, hypothesis, is that what you see in this limited space extends to at least, it's an indication of what you can see if you look at the whole state space of the program. Hope this answers it.
Good. And well, as far as I understood from the paper, you are proposing this disruptive idea, this new idea, but I think that your approach is not, or the vision is not to replace the metrics or the measurements that exist so far, but in some sense to complement them, right?
I think you are perfectly right. So at the moment, we are actually investigating this approach, let's say standalone, because we want to understand what is the potential. But we really see that it could be complementary to what you can estimate, for example, by using software metrics. Because basically, the 2 approaches can solve the problems of the other, in the sense that we look at real facts with our approach. At the same time, if you see, very strange, smelly metrics, it can be a sign of problems that can be confirmed with our approach. So definitely we see them as complementary.
Yeah. And so this is a kind of vision paper. I mean, it's a good idea. You are introducing the idea. Do you think that the industry, will be able to, or will be open to adopt this idea? Is it feasible for them?
The simple question is, and we don't know because we are starting. We of course we hope so. What we see is like that this approach could let's say produce a metric. So you are not going to use the test cases, but you are looking at the metric that you get, like to prioritize which modules of your system you think are the most critical in the testing process. So as far as they can get, let's say the industry people, you can get automatic values that are good for planning. I think they could actually exploit.
Great. Sorry to interrupt. We are just running out of time. So for the audience that they want to continue the discussion, we will be moved, or you will be moved to a discussion room to continue the discussion. Thank you very much.
Thank you, Claudia. Thank you.
Let's continue with the program. Thank you, everybody.